Right, so hello everyone. This is the third lecture on Control and Instrumentation module, and today we are going to study about time response analysis. Now in the previous class you must have, or basically we discussed about transfer functions. Yeah, so transfer function is kind of a equation representing my system, the physical system in S domain, right? So we discussed about that equation, how we develop the transfer function of our physical system. And then we can use that transfer function and implement it on MATLAB or any other simulation software for analyzing our system. Now, I also mentioned that before the first step for developing your transfer function is to convert the time domain equation into complex frequency domain or S domain, right? So one of the advantage of doing that was it simplifies the equation, because in time domain, if you have any derivatives which are very difficult to implement in MATLAB, um, after using or after converting it into S domain, we can simplify it. So our equation, it becomes a polynomial function. Okay, a polynomial equation which can be easily implemented. Right, so that was one of the advantage of converting the time domain function into S domain. Another advantage which I mentioned was in S domain or in complex frequency domain, it helps us to understand the type of system, or it helps us in understanding about the stability or the performance of our system, right? So today in our class, or in this lecture, we will be trying to understand how we can analyze our system or find out stability or performance of our system using the transfer function. Okay, so just by using the transfer function, we will try and identify the stability and performance of our system. Okay, now the first thing that we do to analyze the stability of our system is to find the values of poles and zeros. Okay, so this poles and zeros, they help us identify the performance and the stability of our system. Okay, now what are these poles and zeros, right? What do they mean? So pole, or let's start with zero because it is mentioned the first. So zeros of a transfer function, they are those values of S which makes the transfer function zero. Okay, so values of S which makes my transfer function g of S equal to 0. And poles are those values of S which makes my transfer function infinite. Okay, values of S, let's use this. Okay, so let's take any transfer function, any random transfer function, for example. Okay, let's say my transfer function g of S is S plus 1 divided by s plus 3, something like that. Okay. So we also know that 0 divided by any number is 0, and any number n divided by 0, it is infinite. Okay. Now to make my transfer function 0, first I'm trying to find the values of zeros. Okay. So zeros are those values of s which makes my transfer function 0. Now I'm given with the transfer function. How can I make it 0? If I equate the top line equal to 0, right? If the top line becomes 0, right, then my transfer function will become 0. So in this example, if s plus 1 becomes equal to 0, then my transfer function will be 0. So the value of s is minus 1. So this value of s, it will be called as 0. So for the given transfer function, I have a 0 at s equal to minus 1. Okay. Similarly, poles. So poles of a transfer function are those values of s which makes my transfer function infinite. Okay. So infinite, that means I have to make the bottom line equal to 0. Just give me a second. Yeah. So the bottom line should become equal to 0. So in that case, s plus 3, if it becomes 0, my transfer function will be infinite. It will become infinite. So s equals to minus 3 is my pole of the transfer function. Okay. So I will add one more thing in the explanation for 0. So zeros are those values of s which makes my transfer function 0. That is, which makes the top line or numerator equal to 0. And poles of a transfer function, they are those values of s which makes my transfer function infinite. That is, the bottom line or we call it as denominator equal to 0. Okay. So by equating the top line equal to 0, we find the zeros. By equating the bottom line in the transfer function equal to 0, we find the values of pole. Okay. Now we will discuss how we can, using the values of poles and 0, how we can make a decision whether our system is performing well or whether it will be stable or not. We'll discuss that in the class. Okay. So let's take another example over here. So poles, they make my transfer function infinite. Zeros make my transfer function 0. Okay. And for that, bottom line, yeah. So denominator or the bottom line should be equated to 0, and to find the values of zeros, the top line or numerator should be equated equal to 0. Okay. So let's say this is the transfer function which is given to us. So the given transfer function g of s is s plus 6 divided by s plus 2, s plus 5, 2s plus 9. So if we have to find the values of zeros, what we'll have to do? So zeros makes the transfer function 0, that is the top line or the numerator equal to 0. So the top line will have to equate it equal to 0. So if I equate s plus 6 equal to 0, I will get two values of s. So one of the value will be s equals to 0 from this one, and from this portion of the top line I will get another value of s, which is s plus 6 equal to 0, that is s is equal to minus 6. Okay, so I will get two values here, right? So I have mentioned s equals to 0 and s equals to minus 6. These are the zeros of my system. Okay, now similarly, to find the pole, right? So poles, they make my transfer function infinite, or we have to equate the bottom line now. Okay, the bottom line equal to 0. So the bottom line, we have three terms. Let's write it down: s plus 2, s plus 5, and 2s plus 9 equal to 0. Right? So from this we will get three values of s. So from the first term we will get s plus 2 equal to 0, that is s equals to minus 2. Then from the second term over here we will get s plus 5 equal to 0, that is s equals to minus 5. And from the third term in the denominator or in the bottom line, we'll get 2s plus 9 equal to 0, that is s will be minus 9 divided by 2, or we can say it will be minus 4.5. Okay, so I have written it down, the values of pole. I will have three poles. One will be at s equals to minus 2, another one will be at s equals to minus 5, and the third pole for the given transfer function will be at s equals to minus 4.5. Okay, so like that we find the values of poles and zeros. The only thing in points you have to remember are these. Okay, now so after finding the values of poles and zero, we plot them. Okay, we plot them, and that plot is called as pol-zero plot or pol-zero map. Okay, now pol-zero plot is simply your xy plot. Okay, simply like the xy plot, right? Where your x-axis, it represents the real values, okay, or it is denoted by sigma, and the y-axis is your imaginary axis and it is denoted by j omega. Okay, just that is the only difference. We uh, call the x-axis as real axis and the y-axis as the imaginary axis. Okay, and we plot the poles and zeros, right? I will tell you how to plot them in a short while. We'll take an example, and based on the location, right, location of poles and zeros, we can make a decision about the stability of the system, okay, based on the location of the poles and zeros, right? So let's take an example. So starting from the very basic, first we find the poles and zeros and then we will plot it. Okay, so let's take this transfer function. So the given transfer function g of s is s plus 5 divided by s and multiplied by s square plus 4s plus 8. Okay, so again I will write zeros, they make so zeros are those values of s which makes my transfer function equal to 0, or we equate the bottom line or denominator equal to 0, and poles, they make my transfer function infinite, that is the top line, or we call it as numerator, equal to 0. Okay, so this is the information we have. So let's try and find the values of zeros first. So for the given transfer function, the value of 0 we can find by equating the top line equal to 0. So s plus 5 equal to 0. So that means s will be minus 5. So this is the one and only 0 of my transfer function. Okay, there are no other parts in the numerator, so that's the only one. So I will have 1 0. And now let's find the value of poles. So for finding the value of poles, we'll have to equate the bottom line. Bottom line equal to 0. So s multiplied by s square plus 4s plus 8 equal to 0. Now just by inspecting this equation here, we can get, I think, 3 values. One is from this s and the remaining 2 from this value, from this part of the equation. So obviously, I mean, just by looking at the equation, we can say one of the pole will be at 0 and we will get 2 poles from s square plus 4s plus 8. Okay, so I have solved this in the next slide. So let's have a look at it. Okay, so we have already identified 0 by equating the top line of my transfer function equal to 0. I got s equals to minus 5. Now, from the bottom line, I am trying to find the values of poles. So one of the pole will be at s equals to 0, obviously. For the remaining 2 poles, I have to equate this s square plus 4s plus 8 equal to 0. Right? Now, if we look at this equation here and compare it with the standard quadratic equation. Quadratic equation, generally it is ax square plus bx plus c, right? So if we compare, instead of x, we have s, right? So by comparing the two equations or comparing it with the standard quadratic equation, I can say the value of a is 1 and the value of B is 4 and the value of C is 8. Okay. Now to find the values of S, which makes s square plus 4s plus 8 equals to 0, I have to find the roots of the equation, roots of my quadratic equation. Okay, so I have to find the roots of this equation. Right? So to find the root, there is a very well-known formula, which is minus b plus minus square root of b square minus 4ac divided by 2a. Right? So this is quite well known, and I am pretty sure that you must be aware about this formula. Right. So we already have found the values of a, b, and c. We just have to substitute them. So if we put them in the equation uh, and solve it correctly, we will end up getting this value here, right? S is equals to minus 2 plus minus J2. So basically I will get two values of S. So one of the value of S will be minus 2 plus J2, and the other value of S will be minus 2 minus J2. Okay, so I got two poles from that equation. Okay, so altogether I have three poles at s equals to 0 and s equals to minus 2 plus j2 and s equals to minus 2 minus j2 and 1 0. So 1 0 is at s equals to minus 5. Okay, so just keep these values in our mind somewhere just for the time being, or let me write it down in the next slide, because I am going to plot these values. Okay, so 0 is at minus 5, pole is at 0. Okay, I'll write it down. So I have 0 at s equals to minus 5, and pole I have s equals to 0, s equals to minus 2. Was it minus 2j? Minus and plus 2j. Okay. So plus j2, and the third pole is at s equals to minus 2 minus j2, like that. Okay, so now we are going to plot these values. So obviously we know the pol-zero plot, where the x-axis is your real axis and the y-axis is the imaginary axis. Right? So let's plot zeros first. So 0, they make my transfer function 0, and they are represented by 0 or a circle. Okay, so 0 is, everything is 0. Okay, now pole, they make my transfer function infinite, and it is represented by a cross in the pol-zero plot. Okay, so let's plot zeros first. So 0, one of the 0 was at minus 5. So let's say this is my, I will use the pointer. So this is my 0 axis, right? Origin of my plot. And let's say minus 5 is somewhere here. Okay. So I've put a circle at minus 5, or a 0 at minus 5. Okay. Representing my 0. Now let's plot the values of pole. So one of the pole is at s equals to 0, So at s equals to 0, I have put a cross. Now the next pole is at -2 on the real axis and J2, that is 2 on the imaginary axis. So -2, again I will go in this direction along the negative x-axis or negative real axis. So let's say -2 is somewhere here. Okay. So I will, so -2 plus J2. So positive is upward, right? Positive axis, y-axis or imaginary axis is upward. So from -2 I will go up and I will put a cross at 2, right? So -2 plus J2. Let me just mention that this is -2 on the real axis and this is +2, and let's say this is -2 on the imaginary axis. Okay, so I have put a cross over there. Similarly, -2 minus J2. -2 is here, I'll go down, and -2J or -2 in the imaginary axis is here. So I will put a cross over there. Okay, so quite simple and straightforward. We just have to remember how we represent poles and zero. So zero, they are represented by 0. Pole, they are represented by cross. Okay. So now we have already discussed about this in the previous class, or basically in the first lecture. We have already discussed that the total response or the total output of my system is equal to forced response plus the natural response. Okay. Now what is forced response? So forced response is due to the input, right? Input signal which you are applying, that is external stimulus. Okay. So forced response is because of the input which we are applying, and the natural response is because of the initial condition of the system. Initial condition of the system, right? And the total output or the total response is sum of these two. Yeah. Now, I also mentioned in the first lecture that for the initial time when you start operating your control system, for the initial few seconds, few minutes, or for that initial period, the output or the total response will be only because of natural response. Okay, so let's say we start operating our system from t is equal to 0, and we operated for, let's say, t equals to 5. Let's say some random value, 5 minutes, 5 seconds, whatever. This is the initial period. Okay. So in this initial period, my total response will be only because of natural response. That is the initial condition of the system. And forced response will be 0 for the initial period. And then if we continue to operate our system for, let's say, t equals to some infinite time, maybe 1 hour, 2 hour, 10 hours, like that. Okay. So after this initial period, the total response is only because of your forced response, right? Forced response or because of your input. And then the natural response becomes 0. Okay. So what I am going to do now is I am going to prove this, that if you operate your control system for for a long time, then the natural response becomes 0, and then the output or the total response will be only because of forced response or the input. Okay. So essentially, for getting the actual output of our system, we as a control engineer should wait. We should wait for a few seconds, right? We should wait for the initial time to get over, right? Only then the system will start operating according to our input which we are applying, right? So just you apply the signal and don't take the output. You should wait, let it settle down, and then you should take the output. Okay, because your system generally takes some time to respond according to your input. Okay, so now I'm going to prove that if you wait for some time before taking the output, you will get a good output, and that output will be depending on your input and not on your natural response. Okay, so to prove that, what I have done is I have taken a system, let's say a transfer function, which is s plus 3 divided by s plus 7, right? So this is the transfer function which is representing my system. Okay, so I can call it as system transfer function. And I am applying a unit step input. Okay, so that's my input, that is your R of S. So for step input in S domain, if you remember, it is 1 divided by S, right? Step input in S domain, it is represented by 1 over S. Okay, so I have taken this transfer function and I am applying the input, step input. So the first thing which I do is I find the poles and zero values for both input and output. Okay, so for input, let's find the values of poles and zeros. So input is R of S equals to 1 over S. So there is no S term in the numerator. That means there will be no zeros or no input zeros. Now there is one S term in the denominator. So in that case, the value of pole or the input pole will be at S equals to 0. So similarly, let's find the poles and zeros for the transfer function or for the system. So system G of S is S plus 3 divided by S plus 7. So for finding the values of zeros, I will equate S plus 3, the top line, equal to 0. So that will give me S equals to minus 3. And for finding the system pole, I will equate the bottom line, S plus 7, equal to 0. So that will give me S equals to minus 7. So what I've done is I've written the input pole. I will have only input pole, only one input pole at S equals to 0. And there will be no zeros, no input zeros. and the system 0 will be at s equals to -3, and the system pole will be at s equals to -7. Okay, so I have found the values of poles and zeros for both input and my system. And then what I will do is I will plot them on a pol-zero plot. So my input pole was at s equals to 0. So I have put a cross at 0, right? So I have put a cross at s equals to 0. Now system 0. So system 0 was at s equals to -3, right? So -3 is here. So I have put a 0 over here, or a circle at -3. And the system pole was at s equals to -7. Okay, so -7 is way here. So I've put a cross at s equals to -7, right? So that's my input pole, that's my system 0, and that's my system pole. I've plotted all of them. Now, to find the output or the response of my system, what I will do is I will have to multiply the transfer function with the given input or with the applied input. So my transfer function, it is given as s plus 3 divided by s plus 7. I have simply multiplied it by the input. So the input was 1 divided by s. Now just to recollect from the previous class, we know transfer function is your output C of s divided by input R of s. So if we have to calculate the output, that is C of s, what I'll do is I will multiply it like that. So transfer function multiplied by the input. Okay, so that is what we are doing here. We know the transfer function, we know the input which we are applying. Okay, so we have multiplied them. And upon multiplying, a simple multiplication, so we will end up getting s plus 3 divided by, in the denominator we'll get s multiplied by s plus 7. Okay, so this will be the multiplication we will get. Now what I have done here, I have kind of skipped a step over here. So what I have done is I have applied partial fraction method. Partial fraction method. Okay. So in partial fraction method, you can split the denominator which are in multiplication. Right? I can split it something like this: a divided by s plus b divided by s plus 7, like that. So here they were in multiplication. I've split the denominator and now they are kind of like addition. Okay. Now it's a very well-known method. I have not explained it here, but if you are interested, you can maybe go on the internet and search for partial fraction method, and you can understand it very easily. So since you do not have to do this partial fraction and calculate all that, so I have skipped that over here. Okay, but if you are interested, you can go on the internet and find more about partial fraction method. But essentially what we do is we equate the given equation with a divided by s plus b divided by s plus 7, like that. Okay, and then we find the values of a and b. Okay, so according to my calculation, the value of a, it comes out to be 3 divided by 7, and the value of b, it comes out to be 4 divided by 7. So I've mentioned it over here. After using partial fraction, I will get 3 divided by 7, this whole divided by s, plus 4 divided by 7, this whole divided by s plus 7, like that. Okay. Now, why am I doing that? One of the biggest questions. Why should we do that? Now, if you note the denominator in the first part and the denominator in the second part. So my input R of s, it was a step input. So its value was 1 over s. And the given transfer function is s plus 3 divided by s plus 7. Now if you note the denominator of the input and the denominator of my system, right? Now if I compare them, in the first term, in the denominator I have s, and for input it is 1 over s. So it is kind of, the first term is kind of representing the effect of input on the output, right? So the first term, it represents the effect of input on the output, and the second term here, if you compare it, in the denominator we have s plus 7, and for system in the denominator we have s plus 7. So it is kind of representing the effect of system on output, the second term, right? So we can say the effect of input, that means your forced response, and the second term here, it represents the effect of system on the output. So effect of system, or the initial condition of the system, right? So that represents my natural response, and C of s is my total response. Yeah, so total response is forced response plus natural response, right? Now after that, what I have done is I have taken inverse Laplace transform. So again, you do not have to do that, but in the notes you will find some information about it, so you can refer section 2, page 6, how to convert or how to do the inverse Laplace transform. Yeah, so basically I'm converting the complex frequency domain back into time domain, okay, by using inverse Laplace transform. So if we do that, we'll end up getting 3 divided by 7 plus 4 divided by 7 multiplied by e to the power minus 7t. Okay, so again remember, the first term is my forced response, the second term is my natural response. Okay, so the first term is my forced response and the second term is my natural response, right? Now as t tends to infinite, so in the second term we have exponential e to the power minus 7t, and e to the power minus infinite is 0, right? So as t tends to infinite or a very large number, so exponential, the curve is something like this, right? So this is t and this is e to the power minus something something. Okay, exponential curve is something like that. So as we progress in time, as t tends to infinite, the value of e to the power minus 7t will keep on reducing exponentially, right? As t is going up, e to the power minus 7t is going down. So this value in the second term will keep on reducing, and finally at some point at t equals to infinite, very large value of time, this e to the power minus 70 will become 0. So we can say the natural response will go to 0, or it will become 0. And in that case, the output or the total response will be only because of your forced response, because the second term will become 0. Okay. Right? So we have proved that if we continue to operate our system for a certain period of time, gradually the natural response will go to 0, and we will get the output according to our input or forced response, okay, which we want to check or analyze. Right. So, the next thing which we want to discuss in our class is about poles in second order system. Right. So for second order system, we have already discussed about this equation. So this is the generalized transfer function of second order. Generalized transfer function of second order system. Yeah, this one, where K is your DC gain. So I'll write it here. K is DC gain. Zeta is my damping factor or damping ratio. And omega n is underdamped natural frequency. Okay. We have discussed about this equation. We have kind of used it also in the previous class. Now, if you remember, for a second order system, the step response of the second order system, we could have three options or three different types of output or response. One of the response could be for underdamped system, where your output, it rises very quickly, but there is a overshoot followed by some acceleration before your output settles down. Underdamped system. Then you may have an output for critically damped condition, where the output, it rises very quickly or fairly quickly. There is no overshoot, there is no acceleration, and your system or your output, it get stable around the desired value, right? Very nicely. So this is your critically damped system. And another type of response which we can get is for overdamped system, where again there will be no overshoot, there will be no acceleration, but it takes a very long time, right? Very long time. So this is your overdamped system. So ideally we want critically damped system, because the response is fairly fast. It is not very fast, but it is fast enough. And there is no overshoot, there is no acceleration. It very nicely settles around the desired value. Right? Now, all these values, they depend on the damping ratio, zeta. The value of zeta, it decides whether my system will be underdamped, critically damped, or overdamped. Right? So if the value of zeta is greater than 0, then system is overdamped. If it is equal to 1, my system is critically damped, and if it is less than 1, it is underdamped. We have discussed about this. Now I'm going to make a few conclusions here. Okay, so just bear with me. So all these types of response, it depends on the value of zeta, right? And zeta, if we look into this generalized transfer function of second order, zeta is here, right? It is in the denominator. And if we look at the entire denominator, it looks like a quadratic equation, doesn't it? It is s square plus some constant 2 zeta omega n, it will be a constant, multiplied by s plus omega n square, which will be again some constant, right? So it is quite similar to the equation like ax square plus bx plus c, isn't it? Now let me create some space here. Now, so from this comparison, I can say the value of A is 1, the value of B is 2 zeta omega n, and the value of C is omega n square. Okay. And if we have to find the poles, so poles make the bottom line or the transfer function infinite, that is my bottom line, equal to 0. So to find the pole of second order, I will have to equate the bottom line equal to 0. That means I will have to find the root, because currently the bottom line of the generalized transfer function is a quadratic equation. So basically I will have to use this formula over here, which is minus b plus minus square root of b square minus 4ac divided by 2a to find the roots. So this equation or this formula, it will give me the roots, or I can say the poles of second order. Okay. Now let's take these conditions one at a time. So let's take the first condition, which is overdamped system, and the value of zeta will be greater than 1. So zeta is greater than 1. That means this value over here, 2, the value of b, the value of b, 2 zeta omega n, right? So this will be, let's say 1, it's greater than 1. Let's say zeta is maybe 1.7 or something like that. Okay, any value greater than 1. So b will be 2 multiplied by 1.7 omega n, like that, and c is omega n square. Now I am only focusing on this part of the formula. So b square minus 4ac, right? This will be greater than 0. Now if you look at the equation, it is b square. So b square, it will be 2 multiplied by 1.7 omega n square, and this whole square, minus 4 ac. So a is 1 and c is omega n square. So if we calculate this value, obviously it will be a positive value, because you have 2 here, which if you square it up, it will become 4 omega n, right? So it is already 4 omega n, and we have a multiplication of 1.7 square, right? So obviously the first term will be greater than the second term. So we will get a positive number. That means we can say b square minus 4ac will be greater than 0. Okay, so greater than 0, that means within the square root of the formula, right? Within the square root of the formula, square root of b square minus 4ac, I will get a positive number. right? So if you remember, square root of any negative number, it gives me an imaginary number, right? So since within the square root we have all positive number, so we can say if zeta is greater than 0, I will get two real poles, or we can say two real roots. Okay. Whether it could be a positive number or a negative number, but there will be no imaginary number. Now let's take the second case, critically damped condition, where zeta is equal to 1. Okay, so coming back to the A, B and C. So zeta is equal to 1. Zeta is equal to 1. So B will become 2 omega n, and C is your omega n square. So again, if I calculate B square minus 4AC, I will get 2 omega n, this whole square, minus 4, A is 1 and C is omega n square. So essentially this will become 4 omega n square minus 4 omega n square, that is 0. So in this condition, the value of B square minus 4AC will be equal to 0. Okay, that means if we look at the equation, the formula minus b square root of minus b plus minus square root of b square minus 4ac. So in this case, b square root of b square minus 4ac is 0. So we can say I will get only one real root or real pole. Yeah, because this term is becoming 0. So I'll be left with minus b divided by 2a. So that will give me only one value. Right? It could be again positive depending on the value of b and a. It could be either positive or negative. But it will be real. There will be no imaginary part. Now let's take the third condition, the last one, underdamped condition. So for underdamped, zeta should be less than 1. So zeta is less than 1. That means we can take any value. Zeta less than 1, let's take 0 0.5, 0 0.2, something like that. Okay, zeta, let's take 0 0.5, any small value. So B will become 2 multiplied by 0 0.5 omega n, and C will be omega n square. So from this 2 multiplied by 0 0.5, it will become 1. Okay, so I'll be left with only B is equal to omega n. So B square, if we calculate B square minus 4AC, so B square is omega n square, because 2 multiplied by 0 0.5 is 1, and minus 4A is 1 and C is omega n square. So if we look at this value, the first term is smaller than the second term, right? First term is omega n square and the second term is 4 omega n square. So basically what I will get is b square minus 4ac will be less than 0. I will get a negative value, right? So within this, if you look at the formula, so yeah, I'll create some space. So it is less than 0, that is a negative number. And if we look at the formula again, within the square root, I have a negative value. And that negative value within the square root, it means I will get imaginary numbers, or I can say I will get two complex poles or roots. So complex number is real plus imaginary, right? That is a complex number, right? So depending on the value of poles for a second order system, we can determine whether my system will be overdamped, critically damped, or underdamped. Okay. So I have concluded the results or the discussion over in this slide. So if I have two real roots, my system will be overdamped. If I have only one real root, my system will be critically damped. And if I have two complex roots, my system will be underdamped. Okay. Again, you can use this value p square minus 4ac. So let's say if you are given with a second order transfer function, let's take any random transfer function. Let's say s square plus 4s plus 2, like that. Any transfer function, second order is given. So A is 1, B is 4, and C is 2. So just by, if you remember these, what you can do is just by looking at the transfer function and doing a little bit of small calculation. So let's calculate b square minus 4ac, a quick calculation. I will get 4 square minus 4 multiplied by 1 multiplied by 2. So 4 square is 16 minus 4 multiplied by 2 is 8. Right, so basically I will get a positive number which is greater than 0. So I can say for the given transfer function, my system will be overdamped. So you can see how quickly we can decide whether our system will be overdamped, critically damped, or underdamped. So just by looking at the transfer function and doing a little bit of calculation, small calculation, we can determine whether it will be what type of system. Okay, so it is kind of a shortcut method, right? So it is kind of a shortcut method to determine the condition of my system or the performance of my system. Or if you know the poles, value of poles and zeros, the poles of second order, again you can decide. Based on the value, if you get two real poles, it is definitely going to be overdamped. If it is only one real pole, that is, it will be a critically damped. And if it is two complex poles, you will get, or the system will be underdamped. Okay. Now, continuing with the discussion on poles in second order system, let's now visually uh, try to have a look at the poles, how they will or what will be their location on the pol-zero plot if the system is overdamped, if it is critically damped, or if it is underdamped. How the location of poles they get changed for the three types of responses or the output of second order. So for that, we have taken an example over here. So the transfer function is 40 divided by s square plus 5s plus 4. And if you compare it with the generalized transfer function and find the value of zeta, it will be 1.25. That means it is greater than 1. So my system will be overdamped. Okay, in this condition. And again, by using the formula minus p plus minus square root of b square minus 4ac divided by 2a. That formula. I have found the values of poles for my second order system. And I have used MATLAB to plot the values of pole. So pz-plot is a function which I will be demonstrating as well. But using that, you can plot the pol-zero plot for any transfer function. So anyways, so these are the values of poles and they have been plotted on a pol-zero plot. So minus 4 is here and 0 is here, right? So one of my pole is at minus 4. So I have put a cross over here. So 0 is over here, right? So I have put a cross at minus 4. The second pole is at minus 1, which is here. So I have put a cross at minus 1, right? So when the system is overdamped, my poles, they are wide apart, okay? Now, in the second example, I have taken the same transfer function 40 divided by s square, but the only change which I have made is in this value. In the previous equation, it was 5s. Apart from that, everything is the same. In the previous example, it was 5s. Now I have reduced it to 4s, right? So that will make my zeta value equal to 1. And then my system will be critically damped. And upon calculating the value of pole, I will get one pole at s equals to minus 2. Okay, so 0 is here and minus 2 is here. So I have put a cross at minus 2. This is the 0x axis. Okay, so I have put a cross over here, right? So basically what is happening is when my system was overdamped, the value or the location of poles, they were wide apart, and when the system becomes critically damped, they kind of merge. So the point that I'm going to make here is this value of pole is not a single value. Essentially, it is two poles which are overlapping each other, right? So basically, for critically damped system, we have two poles with the same value, right? So for critically damped system, we have two poles with the same value. And that is why in the pol-zero plot, they both overlap. To demonstrate this, in the next example over here, I have taken a value slightly greater than 4, right? Something like 4.001. So in that case, my system will be almost critically damped, or I can say it will be slightly over damped. Yeah. So in that case, I will get two values of pole. So one of the value of pole will be slightly smaller than minus 2 and the other one will be slightly greater than minus 2. Okay. So in the pol-zero plot, if I continue to reduce the value and bring it closer to the critically damped value, what I will see is the value of poles, it will keep on reducing and it will be finally at minus 2. So essentially what is happening is when your system is over damped, your poles are wide apart along the real axis. And as you bring your system closer to critically damped condition, these two poles, they come closer to each other. And finally, at critically damped condition, they will overlap each other. Okay. Now, the last type of system, which is your underdamped system. So again, if you notice, I have taken the value, I have reduced the value from 4 to 3. Okay, so that makes my system underdamped. So zeta value is coming out to be 0.75. Again, I have taken out the values of poles. We got two complex poles, and if you plot them on a pol-zero plot, so this is my 0, and along the x-axis or on the real axis minus 1.5 is here. Okay, so I have plotted minus 1.5 plus 1.32 and minus 1.5 at minus 1.32. So those are the location of my poles for a underdamped system. So finally, to conclude all the things which we have discussed, what happens is when the system is overdamped, my poles are wide apart. As we bring it closer to critically damped, the poles, they move closer to each other along the real axis. And finally, at critically damped condition, they will overlap each other. And then if we continue to reduce the zeta value or the damping ratio, uh, and the system becomes underdamped, they spread across the imaginary axis like that. Okay. So that's what happens with the location of the poles in the three responses or in the three types of systems. Now we have already discussed this in the first slide and in the previous classes. If you have an overshoot with some acceleration, that's your underdamped, the blue curve. And if your system response is the ideal response, that is, it rises fast enough and there is no overshoot, no acceleration, that's your critically damped condition. The brown curve and the green curve, it represents the overdamped condition. Again, in overdamped condition, there will be no overshoot, no acceleration, but the main concern is the long time which it takes. Okay. Now, this is the response of your second order underdamped system. Okay, so for underdamped system, actually we have already discussed this about the rise time, peak time, settling time, but we know only the definition or the statement or what they mean. So today what I'm going to do is I'm going to introduce you to the formulas for these values, how to calculate them. So just to discuss it or revise it very quickly, the second order underdamped system, the response, it starts from 0 and it goes up to the desired value, but you will have some overshoot followed by some acceleration. Before your output or your response, it settles down around the desired value. Now the desired value is 1. So desired value is 1. Now rise time. So rise time is the time which your system takes to produce or to rise from 0 all the way to the desired value. Okay, so this is the rise time. Peak time is the time taken by your system to reach the maximum value. Maximum value could be anything, whether it's not the desired value. In this case, it is slightly greater than your desired value. Okay, so that's the maximum value or the peak, right? So the time taken to reach the maximum value is your peak time. And settling time is the time after which your response stays within the desired range. So desired range in this graph, it is highlighted by the blue line. Okay. So this is my desired range. Obviously, we cannot have an output which every time is the same. It can be around that value, but it is very difficult to tune our system and get the exact value every time. Right? So that is why we choose a range of value. So after this time, if you see my response or my output, it stays within the desired range. Right? So that time after which my output stays within the desired range is called as settling time. And of course, you will have some steady state error. That is a difference between your actual output and your desired output. So now let's have a look at the formulas for these values. So rise time, again you can represent it by capital T R or small t r. It is essentially the same thing. Okay, so in the graph I've represented it by capital T. In the formula I'm representing it by small t. So don't get confused by that. So TR is given by the formula. I think should be visible for you. Similarly, you have the formula for peak time, settling time, percentage overshoot, and damped natural frequency. Now, damped natural frequency is omega t, and it is different from omega n. Omega n is under damped natural frequency, right? It is different, so just don't get confused over here. Now if you look at all the formulas which are there on your screen, we could see that all these to calculate all these values we would need zeta, which is your damping ratio or damping constant, right? And omega n, zeta, this is again zeta, omega n, zeta, zeta, omega n, zeta, right? So for calculating these values, we would need omega n and the value of zeta, that is your damping ratio, right? So this can be found by comparing the given transfer function with your standard or generalized transfer function of second order. Okay. So step number 1 for solving or for using these formula would be to calculate the value of omega n zeta by comparing the given transfer function with the generalized transfer function of second order. First find the values of omega n and zeta and then use the formulas to calculate rise time, peak time, settling time and all. Okay, so let's take a look at one of the question. So in this question, we have to find the value of rise time, peak time, settling time, and basically all the values for which I have given the formula. Okay, so we have to find all those values for second order system. So the transfer function is given here. G of s is 100 divided by s square plus s plus 5. Okay. Now, as mentioned, the first step would be to compare the given transfer function with the generalized or the standard transfer function of second order. And find the value of omega n and zeta. Okay, so if I compare the two transfer functions, if I compare the last term, so omega n, last term in the denominator, I'm comparing. So omega n will come out to be equal to omega n square will be 4. So we can say omega n will be square root of 2. Now if I compare the second term in the denominator, so it will be 2 zeta omega n will be equal to 1. We already know the value of omega n. It is, sorry, it is square root of 2. It will be 2. Right. So, yeah. So we already know the value of omega n. So zeta will be 1 divided by 2 omega n, or 1 divided by omega n is 2 divided by 4, or we can say 0.25. So like that, I have found the value of zeta and omega n. Now in those formula, we did not need the value of DC constant k, right? So I'm not calculating it. But if you want, you can compare the numerators and find the value of k. Okay. Now, apart from these values, I have also calculated square root of 1 minus zeta square, because I will be using this value very often in the formula, and it came out to be 0.968. So now let's start calculating the value. Let's calculate the rise time. So rise time is given by this formula, and in this formula we need the value of omega n and zeta, which we have already calculated. So omega n was 2 and zeta was 0.25. So I've simply substituted the value. If you carefully calculate the value, you would end up getting 0.9416. Since TR is your rise time, so its unit will be seconds. Now there is a MATLAB function which gives you basically all these values: rise time, peak time, settling time, and all, right? So if you put in your transfer function, it will automatically give you all the values. So I've compared the MATLAB values, or the values which I got from MATLAB. So from MATLAB I got 0.943 seconds, which is quite close. Now, similarly, the next thing which we have to find is the peak time, right, which is given by this formula. So again, we know the value of omega n, which is 2, and zeta is 0.25. Now, if you notice, it is square root of 1 minus zeta square. Since I have already calculated this value as 0.968, right? So I'm directly using that value. And it came out to be, if you do the calculation, the peak time will come out to be 1.62 seconds. And from the MATLAB, again using the function step in for g, the value it comes out to be 1.0 6566. Close enough. The next thing which we have to find is the settling time, Ts. So for that again you will need the value of zeta and omega n. Simple substitution, and if you do the calculation you will end up getting 8 seconds. So again, using step info G, it comes out to be about 7.05. A little bit of difference is there, but okay enough. Just a difference of 1 second. Then the next thing we have to find is the percentage overshoot. So percentage overshoot, it only depends on zeta values. Okay. So again, simple substitution, zeta is 0.25, and we have already calculated square root of 1 minus zeta square, which is 0.25. Its value is 0.968. So we have used that value. And again, if you continue solving it correctly, you should end up getting 44.4%. So it is percentage overshoot, so unit will be percentage. Now from the MATLAB, I got that value to be 44.3, quite close, right? And finally, if I calculate the value of omega d, which is damped natural frequency, again we know the value of omega n, it is 2, and the square root of 1 minus zeta square, we have already calculated the value, so 0.968. I have directly substituted the value, and it comes out to be 1.936, and the unit of omega, omega, it is radians per second. Okay, so just remember the unit and don't forget to mention the unit. Now this value is not given by the function which I was telling you about, but what you can do is you can measure the time between successive peak. So for underdamped system, basically you would have this kind of a response. You would have some oscillation like that. So you can measure the time between two successive peak, right? And I have done that, and it comes out to be 3.32. And from that, I have calculated the frequency. So frequency is 1 over time. So I got 0.3096 Hertz. And then you can use omega is 2 pi f, which is 2 pi. I have already calculated the frequency. So this value upon this calculation from the graph or from the response of the system, it comes out to be 1.95, quite close to the calculated value. Okay, so again, if you are given with the transfer function, you can calculate all those values, or if you are given with the response, the graph of your output, again you can calculate all these values from the graph also. Okay, so this is the response of the system or the transfer function which we were using in the previous example, and I have plotted all the relevant values over here. So basically you measure the time difference between these two successive peak to calculate the frequency, and you can then calculate the damped natural frequency omega d from the graph. Okay, So this is all which I wanted to discuss or cover in this class. We will come down to the tutorial questions, but before we go to the tutorial questions, let me quickly demonstrate the MATLAB functions which I was talking about. So, okay, so let me zoom in a little bit over here. So in the last class, we have already discussed how we can implement a function, a transfer function in MATLAB. So in this class, basically I've taken the second order transfer function, which is 54 divided by s square plus 4.5 s plus 9. So in the numerator, I have 54. So I have taken it here. And in the denominator, I have 1. The first value is 1. The second value is 4.5. And the third value is 9. Okay, so I've written it within the square bracket as 1 space 4.5 space 9. And then using this function tf, and within small brackets, if I write numerator, which is the numerator of my transfer function, comma, denominator, it will give me, or it will automatically generate the transfer function of my system. Then I have applied a unit step input. So for doing that, I am using this function step, and within bracket u represents the magnitude. So in the example, I have taken the magnitude to be unity or 1 multiplied by the transfer function g. Okay. Now I have used this step info g to calculate all the important values, right? So let's run this code and see what all values it gives us. Okay, so I've also plotted the pol-zero plot, and actually this is the response of my system. And let's see what all values of uh, what all important values this function step info g it gives us. It gives us the rise time, the settling time, the transit time, settling time, and minimum and maximum values, overshoot, undershoot, peak value, and peak time. So basically most of the values it gives us this function step info g, right? So step info, and within small bracket, if you mention the transfer function g, okay, then it will give you all the values. Now I have also plotted the pol-zero plot. So for plotting the pol-zero plot, you can use pz plot, and within brackets again you should mention the transfer function. So since we have run the code already, so as you can see, this is your pol-zero plot. So it has very nicely plotted the crosses representing the poles, and if your system has zeros, it will also plot the zeros. Okay, so currently it was a second order system with no zeros, so it is plotting the two poles like that. So you can use these functions uh, for developing your model or for analyzing your system. Okay.